It's a pleasure to see you again after 36 hours of intensive competition and the contest. Finally, we have some additional activities that we prepared with our partners and co-organizers. And we will start with a session provided by our good friends from Yandex. And today we have a lecture by Sergey Ovcharenko, who is Neural Networks for Computer Vision Team Lead at Yandex. So without probably any further introduction, I passing the words to Sergey. Thanks a lot.
Yeah, thank you, Sergey. And hi, everyone. Let me just share my screen. Yeah, here we go. So my name is Sergey, and I lead the deep learning or neural networks for computer vision team here at Yandex. And today I'm going to discuss our approach that we take to analyzing the videos. So let me just start with some brief outline of the talk. I guess I'll start with just briefly mentioning all the tasks and all the problems that we face in terms of analyzing video data. I'll go through the available data and then spend some amount of time on describing our main, workhorse, our video model. Then I'll go into some more details on some more, product related stuff and technologies that we build. Yeah, please feel free to, interrupt me and ask questions along the way, but I guess we'll have some time for a dedicated Q&A session in the end. Yeah, okay. So what does actually video analysis mean for us? What are some of the tasks that we are trying to solve? Well, first of all, search is makes a big part of Yandex's business. So ranking videos and text to video retrieval is of large importance for us. But there are also a number of other interesting tasks like video recommendations, video classification and tagging, which in my mind falls into two broad categories. Like you'd like to, just describe a video as a whole and assign it some label, like whether it's a movie or a TV show, or whether what's the main semantics of the video. And the other category is that you'd like to detect some unwanted activity in the video, like, I don't know, alcohol consumption or some cases of violence. This might sound that the two of these tasks are quite similar, but actually from the machine learning perspective, they can be quite different. We also do duplicates for video detection, and we also do highlight detection, which is basically extracting some most meaningful, most interesting parts of the video. We also did quite a lot on generative modeling for video, like video super resolution, but I'll just touch that briefly in this talk. Yeah, well, it's pretty clear that for most of these tasks, you need a good model for a good network, which will be able to extract some great and meaningful embeddings from the videos. I've listed some of the requirements for such an embedding here. Basically, we want it to be multi-domain. We don't want to, our algorithm to specialize on some special set of videos, like the how-to videos or movies or whatever. We just want it to be able to handle everything. it should also be robust to various video lengths, because we try to analyze all of the videos that are out there on the internet, and they vary greatly in length. It should describe the full video in like one vector of numbers, and this vector of numbers should be quite short, because like we measure the number of videos in millions or even billions, and well, storage space and RAM on the machines is limited. So in order to do, let's say, fast nearest neighbor search or something, you just have to pack a lot of videos into some limited space. Yeah, let's discuss some of the data sets that are out there. Well, when we started these projects, mostly these data sets were available, and unfortunately, they have all some common problems. Like they're either small or they cover some narrow domain. In case Even in case of a narrow domain, there's sometimes little interdomain variation. That is like, for instance, if the video falls into a sports category, it might be some specific kind of sports there, and so it doesn't cover all of the variation of the videos that are out there. Often videos come in short segments or have fixed length. Somewhere along the line of the project, the YouTube 8M dataset came up. Um, Actually, some earlier versions suffered from some of these problems too. But we actually are looking closer at this data set right now. Anyway, we set up at building our own in-house data set. We had the video search engine at our disposal. You can think of it um, as a black box where the user asks queries and is presented with a number of videos that the search engine deems relevant to the query. There are several ways that you could use such a tool to collect a data set. Well, first of all, and maybe the most straightforward, is to just get a bunch of queries and scrap the search engine top results. You could then use some extra information there, like get the user clicks, the videos that the users actually clicked on for some particular query. And finally, what we did, we used the deep views by the user, namely, we kind of sampled the videos that were watched by the user for some greater extent. Let's say like 75% of the video was watched by the video with respect to some particular query. And yeah, that's where we actually ended up with, because like when you just get the top results from the search engine, the data is actually too noisy and you kind of not getting some extra signal there. You're just replicating the same ranking that you have. The user clicks, if you think about it for a moment, is actually quite noisy too, and usually the users don't see the video itself before clicking on it, right? The user just sees the thumbnail or some live preview, so it provides poor information on the correlation between the query and the actual video content. On the other hand, the sampling videos according to how long the user watched the video is mostly clean data. It's labeled by a lot of humans users, and we sampled like more than 100 million videos, about 200 million queries, and got about 1 billion positive samples in such a way. The thing is, if you think about it, that the only kind of ground truth labels that we have are the positives. We don't really have negatives here, because for some particular query, the video might have not been showed up, or the user might have clicked and watched the video in some other circumstances. So yeah, in order to get use of this data, you should mine some negative samples, which is usually a tricky way, but we'll discuss it in some more details later on. Okay, basically some really high level overview of the approach we took is that we have two modalities, right? We have the queries, which are essentially text, and we have the video content. What we did is build two separate networks. One network deals with the text input, the queries, which is just actually a projection of a bag of words. And one other network produces the embeddings for the video content. And basically the text and the video features are projected into some shared space where we try to build a distance matrix in some semantically meaningful way, so that, let's say, the queries that contain the word cat might be close to the videos about cats, and so on. Yeah, let me just stop here for a moment and ask if you have any questions up to this point, because we are going into some more technical details later on. Okay, I guess not. Okay, let's move on then. So yeah, this type of task is actually known as the metric learning in in the community. What we started with was the quite common triplet loss. Let me just spend a couple of minutes and explain what is this triplet loss all about. In our case, the triplet is the multimodal thing. You sample something that's called an anchor, which is actually a query in our case, and you also get sample two videos. One is a positive sample, and so that's basically some video that the user watched to a great extent, and the other is a negative sample, which you have to somehow come up with. Now, if you look at the bottom picture, like let's say at the start of the learning, your negative sample might be closer to the anchor than your positive sample, since the network is randomly initialized. And they are all on a circle because we normalize all the embeddings and are talking about cosine distances here. And throughout learning, what you want to achieve is to bring the positive samples closer to the anchor relative to the negative samples. So to push negative samples further away than the positives. Now, in order to do this, people at some point came up with the triplet loss. Yeah, it was, to the best of my knowledge, first used by the FaceNet paper by Google, which is, we have the graphs plotted here on the right, where on the x-axis is the distance between the positive and the difference between the distances between the positive and the negative samples. Yeah, you basically subtract the distance to the negative sample, from the distance to the positive sample, add some margin alpha, which is on the plot is the distance between 0 and the that point where your piecewise constant function becomes 0. And you basically take the positive part of this whole thing. Now it's quite clear that the triplet loss has some disadvantages, namely the gradients are 0 when the negative sample is further away from the anchor than the positive plus this margin alpha. And people at Yandex came up with something called dist log at some point in time, which is like a smoother approximation to the triplet thing. And there's also this parameter alpha, which actually controls the smoothness of this curve, right? So the dist log loss is plotted in green here. And well, its probably main advantage is that you could get those nice gradients from the samples that are far away in terms of the distance from the anchor, which you didn't have in triplet loss. Now, okay, since our data set doesn't have the dedicated negative samples, we have to mine the negative samples. We do it in an online manner, basically mining the negatives from the batch. That's why we actually need some reasonable size batch sizes, like 2,000 or something, or 4,000. Now let me describe the way we do it. Let's assume that the axis here is the distance to the anchor, and the positive sample sits right in the middle here. You could break all the negative samples into 3 large categories. The hard samples are those that are closer to the anchor than the positive. The semi-hard is something that was used by the original FaceNet paper, that are the negative samples that are further away from the positive, but like closest to the positive, right? So it's basically the limit to the positive from the right. What we ended up using is what's called reverse semi-hard. That's actually the hard negatives, right? In a sense that they are closer to the anchor than the positive, but it's like the least hard of all the hard negatives. What's the most important to in this slide, I guess, is that there's some tricky mining procedure, and actually that adds some extra limitation on the types of architectures that we're going to use. And I'll describe those on a couple of next slides. Like here's what most of the people doing video analysis do like these years, I guess. You might use like 3D convnets, maybe pre-trained ones, or you might apply a regular convnet to an image, then use the optical flow from some consecutive frames, pass it through a convnet yet again, and then aggregate it using the 3D convnet or just some other aggregation method. So that's basically some of the ways that you could incorporate, temporal information in your model. Now, the good thing about these approaches is that really like zero information is lost here. It naturally captures motion or whatever temporal structure there's in videos. Unfortunately, there are also some disadvantages. Well, that first of all, the 3D convolutions are painfully small and they require a lot of GPU RAM, and that actually prohibits to the usage of large batch sizes, which is important for our method. That's why we took another approach where we take like some predefined number of frames from the video. We extract the features by using just plain convolutional neural network feature extractor. And then we train some video model on top of these features, right? And we don't propagate the gradients to the feature extractor network. That in such a way, we decouple the feature extractor from the video specific model, and we can train fast, which is essential with the data set sizes that we have. We can use large batch sizes for to mine some meaningful negatives, but it also has some drawbacks, like it actually loses the time information, right? You have this dependency on the backbone feature extractor, and it actually makes your your pipelines, the data pipeline and your training much more complex and error prone. Still, that's the approach that we took. We've experimented with a number of ways to aggregate the frame features. We used bidirectional LSTMs, the 1D convolutional networks, and we also did a lot of experiments with transformers. Now I have some of these experiments listed here in the table. Now there are two main metrics here. One is a number of hard triplets among some randomly sampled 64 triplets, and basically the less is better. Like that's actually a number of, you might call it the misranked samples, right? So ideally you want this number to be 0. The other is the score from the Yandex video ranking algorithm, which doesn't really make much sense to describe here, but the main thing to know is that the more is the better. Right? Yeah, so the BLSTMs worked really great, especially when you add more data and increase the size of the batch and the size of the network. But then the convolutional neural networks did even better. The transformers were pretty close to the convolutions, but still not quite there. But I think that we'll be able to push it beyond the convolutions, I guess. All right. It's maybe, I guess that's all that I was going to tell about the our video feature extractor. In case you have any questions, now might be a good time to ask them. Okay, still no questions. That's probably everyone understands what I'm saying. Okay, anyway, let's move on. Yeah, what this algorithm does is actually to extracts one embedding per video, which is good for some tasks because it's easy to use. You have a video and you have a corresponding embedding. Unfortunately, since this embedding is fixed size and the videos vary in length like a lot, it has some drawbacks. First of all, it sometimes well, it's obviously it fails to capture some fine nuances of long videos. It also has troubles describing videos that are actually a set of other disjoint videos. That's like uh, when each part of the video is some kind of semantically separate scene. It's hard for you to describe it with just one embedding, and it's also hard to do like segment analysis, like what's going on in the beginning of the video, what's going on in the middle of the video, or in the end. That's why we thought that we probably need a local descriptor that should also be fixed size, but it should also describe some, not the all of the video, but some self-contained period. And ideally, it would be constructed in such a way that the global embedding is some kind of an aggregation or pooling from a set of local descriptors. Right. Now, in order to build such a thing, we first needed a way to to cut the video in some semantically whole parts or scenes, and we ended up with an algorithm for scene cut detection. The first iterations were trained in an unsupervised manner. What we basically did is that assume that the axis is the time of the video here, and we sample 3 parts of the video, namely the query, like the positive one, which is adjacent to the context, which is just some 30 seconds of a video, and a negative video segment, which is further, which is quite like sometime further in future. So we assume that the negative part is part of some other thing, while the positive sample is essentially the same scene as the context. We aggregate the features and pass them through the neural network, and basically the neural net's task is to classify whether the scenes changed or didn't change between the context and the and an adjacent piece of video, right? Now it actually produced some nice results. We collected a data set of like 50 quite diverse videos, and the way we measure it is that we ask the Turkers, the guys from Yandex to label each point presented by the algorithm, whether it's indeed the change of the scene or not. So if you think about this procedure for a moment, it's quite clear that that it's difficult to measure recall here, since we don't have like any an exhaustive set of all the scenes, of all the places where the scenes change. We could just probe some of the algorithm's prediction. So we use the number of predicted points as some proxy to recall. Anyway, what we observed is, what we were concerned here is the precision of this algorithm. And for reference, the just randomly cutting a video in scenes is like 3% precision, which is just noise from the labeling procedure. Now our baseline CNN model gave the precision of about 23%, which improved greatly when we used multi-head attention there. And then we also labeled a small data set and added the audio features and fine-tuned our algorithm just a tiny taste on this small label data set, which gave the precision of 73%, which actually is quite nice and worked really well. Now, yeah, once you have the, a way to cut your video into some scenes or some semantically connected components, and you have a way to, describe each of these components with an embedding, you might do some nice stuff like, detect highlights, extract some parts of the video, and so on. And then that's what our highlights project was about. Like there's actually kind of a domain mismatch between the videos that were hosted on Yandex and the videos that people like to watch. Like most of the videos that people tend to watch are on some social media are fairly short these days, and it's some funny and short content. Besides, we did that for Yandex Zen, where it's actually a blogger platform, and quite a lot of videos there are short and entertaining. While the typical videos that were hosted on Yandex were like 20-40 minutes long, and devoted to some particular topic or just a mixture of topics. And we decided it would be a nice idea to extract the most interesting, the most prominent part of this longer video, and just show it to the user. And in case the users get hooked up, we might show a button like watch more or watch all of this video, and so on and so forth. Yeah, and that's how we did it. Now, actually, once you have the scene cut algorithm, you just get this long video, you cut it into disjoint scenes, and the way you can look at this problem now is that what parts of the video to merge, so that some longer highlight emerges here, and the way how do you combine these scenes. Now we did so yeah, we obtained the separate scenes for each video. Then we added the embeddings for these scenes. We did some dynamic programming and heuristics to build the set of highlight candidates, added a number of features for the candidates, like the embeddings, the video embeddings, some per frame features, and so on and so forth. And we trained CAD boost, so we trained gradient boosting to obtain like the scores, the probability that the user will watch the video to the end. So we kind of started showing those generated highlights and observed like which highlights the users like the most, and trained a ranking algorithm on that data. The fun thing is that we managed to get some nice results with this quite simple approach. Yeah, I apologize for the Russian title here. I just took a screenshot of our graph platform here. Yeah, so basically what's on this graph is the comparison between the um, like the average videos that are on the on some of our servers, that's red and blue, and our generated highlights are green, and on the y-axis you have a number of the percentage of what we considered good views. That's actually the percentage of the videos that the user watched to the end, or push the button that I liked it, I want to watch the whole of this video. And it basically turns out that even our highlights were basically on par with the original videos, which can be partially attributed to the fact that they are just shorter and easier to watch to the end. But that's not all of the story. So I guess the highlights did a great job here. Um, yeah, let me then just move on to some other project that we did in terms of video analysis. Yeah, once you have this the embeddings, we decided that we have to train a number of classifiers. And you might think like, what's the big deal? It's 2021 and you have a feature extractor and just train a neural network on top of the embeddings and get your classifier. It's not that easy for video data, because videos are like really a pain to label. And besides, the classifiers uh, can be broken down into two categories, as I mentioned. Like, first is probably the easier one. You just have to assign a label to the video as a whole, whether it's a video about travel or DIY or cars or whatever. That's something that our general purpose embedding is great for. It just captures like what the video is all about notion really nicely. Some other task is actually moderating videos, and that is detecting violence scenes, hate speech, and whatever. And what's difficult here is that you have to get the right label. If you have an episode of smoking for 2 minutes in, say, a 2 hour long video, that's really hard to do with a single embedding, and we had to employ some additional tricks there. Um, yeah, there's also one other thing that helped us a lot here, and that's actually the active learning approach. Now, the way we did it is we deployed this classifier, and since mm, we label a lot of videos with it, uh, we um, we cannot measure recall on this whole large set of videos. We can only measure recall on some smaller labeled set that we had labeled by the Turkers. Uh, but still, there were some mistakes, and we came up with what I believe a clever procedure for actively mining the samples that where our model could do a better job. We basically sample a number of videos and observe like what been in terms of the probability of containing the of coming to this particular label does this video have according to our classifiers. And here it's, and then we label some of the videos that are, according to some threshold, are most probably false negatives and false positives, and we just label them and add them to our training set and get some quality improvements there. Yeah, and some of the lessons that we've learned there is that the video is really hard to label, as I mentioned. Like the Turkers always get the video wrong, and besides, it's just quite expensive to label long video sequences because just people have to watch it. Now the data matters the data always matters, but it's especially right for doing video analysis and classification. And for some cases, you have to take into account both the local context, like what's going on in that particular point in video plus minus like half a minute. And you also have to consider the global context, like what's all of the video is about. Now, yeah, as I mentioned in the beginning of the talk, we also worked on video super resolution. I'll guess I'll describe just some interesting challenges that we faced in the end there. Like first of all, we trained the GAN-based model, which like I guess produced nice results. We measured the results in terms of side-by-side comparison with the original by the Turkers yet again, and we kind of ended up with models that were producing like 90% of the win rate over the original videos. Like what we observed here is that there's actually a trade-off between the ability, the win rate, and the appealing look of the video, and the way like how natural is the video. So basically we built some plots like this. We like on the y-axis here is some measure of how the video is natural, and on the x-axis is the win rate in terms of how Turkers labeled it. And you can observe that and each point is just some network that we train throughout our experiments. And you might notice that the kind of most of the networks lie on this line from the top left to the bottom right corner, which actually means that it's quite easy to train some network that the people will like, and it will win against some original videos or some, in this case, our earlier model. But the more visually appealing it is, the less natural it is, since you lose like the y-axis here, which is the measure of how natural is the video. And our main task here was to push for the networks that are in the, like, say, top right corner here, but it's the whole Pareto front here that we had to experiment with. Yeah, I hope that I didn't lose everyone with this final part. And so, yeah, thank you for your attention, and congratulations. So if you have any questions, I'll be happy to answer them.
Thanks a lot, Sergey, for your wonderful lecture. So if any of you have questions to Sergey, please ask away. Actually, you can write to the chat box, or you can even switch on the microphone and ask it orally.
Yeah, I see there's one question in the chat. Didn't you try to produce negative samples yourself by concatenating different video clips? I'm not sure whether like what model are we talking here? Like okay, right. Thank you. So yeah, that's actually, I mean, that's what we did in a sense, right? So we let's say here's your long video. You take this piece of video, and then the way it was trained, the way the training samples were constructed, we take an adjacent piece of video and say, okay, this is the same scene. This is a positive sample. Then we take some video sample further away from the context of the query and say this most probably a negative sample. It's like 2-3 minutes away from this one. That's most certainly a negative sample. So we concatenate it and say that that's a negative sample. So in a way, that's basically what you propose, right? So we concatenate different parts of the videos, and that's just negative samples. And if you were talking about like using totally different videos for negatives here specifically, we might have tried it, but I guess that would be a much easier task for the network, because it would be really easy for the net to overfit to specific lighting conditions of camera or post-production that's done for most of the videos, right? So I believe that the mining negative samples from the same video sequence is harder and better than combining from like combining synthetic negative samples from different clips.
Thanks a lot. Maybe any other questions so far? So seems like there are no questions.
Okay. Yeah, thank you for your attention then, and good luck, everyone.
Thanks again, Sergey, for a wonderful lecture.
Thank you.